So I'm going to try to follow Tom's talk. Tom's a hard guy to follow, and
Really? The other Tom.
the other Tom, yeah, the other Tom. Oh, they both are really. But I do want to say, for those that know me, and I'm being careful in this talk, I've had another vertigo attack this weekend. So the third one I've had. We're working with a doctor and all that. So that picture that Tom had of "Are you drunk?" that was a picture of me trying to check no. I'm just really, really dizzy.
We do. It was somebody trying to check.
That's right, yes.
I recognize the handwriting.
Yep. So as we get into millimeter wave bands and higher frequencies and keep going and moving, we're always trying to build new gear and trying to build new stuff. And the question is, well, am I even on the air? Am I even on the right frequency? Especially if you're by yourself in an area where there's no other operators on a given band and you want to get something started. You kind of have to build a transmitter and a receiver simultaneously. And along the way, you're going to have problems. You're going to want to check, well, you know, what's going on. So a spectrum analyzer is a great thing to have. A lot of us have spectrum analyzers of different kinds. The commercial world provides us with a lot of external mixers that are on the surplus market that connect to the spectrum analyzer, and they allow you as a user to look, you know, in a waveguide band or two with a spectrum analyzer. And even if you don't have a fancy spectrum analyzer, you can certainly use an external signal generator as an LO and use a harmonic of it. And we'll get into that and how you can use some of the mixers and such that are out there to give you a spectrum analysis. So we'll cover basically just simply what a mixer is, a little bit about waveguide. This will all tie together in the end. I'm going to look at two most common surplus waveguide mixers that are out there for test equipment, a la eBay or Hamfest. We'll review the designs. We'll dive into both of them a little bit and see what makes them work and not work. And we'll look at what the options are to expand the application of one of them and an alternative option. So basic mixer, nothing real fancy here. If you're on 78192, one of the East Coast guys for that band, you'd have a mixer and you want to down convert to an IF. Well, if I want to use a 432 IF or so, I could use an LO at 77.76. Oh yeah, sure, I've got a 77 gig generator on the bench, right? Don't you? Just use it, right? Just set up a test mixer. And I need a regular mixer too, so probably not going to work very well. But the important thing to understand is that in a fundamental mixer like this, the loss, the insertion loss, is about 6 to 10. Depends on the type of mixer, depends on how well you're driving it with LO power. So RF to IF, anywhere from 6 to 10. What's a harmonic type? Well, you can use a standard mixer as a harmonic mixer by simply pumping LO power in at a fraction of the LO frequency that you'd really want if it was a fundamental mixer. So in this case, you can divide by any number. You can divide by 2, 3, 4, 5, 6, 7. There are some limits. You can use, again, as up or down converters. And there's your formula. All we're doing is putting an N in front of the LO. And the loss is proportional to N. Ideally, it's N squared, unless you're me. In that case, you build a real crappy mixer, or you just try something and you find out the conversion loss is 40 dB and it doesn't match the theory. Who cares? I'm on the test bench. I don't really care. I just want it to work. Okay, shifting for a second, waveguide. Everybody's seen these plots and pictures. They're all over the place. I just want to, we'll tie this together with all this in a minute. This is background. The basic common mode, TE's 1.0 mode we use in waveguide, and this is our rectangular guide here. RF is propagating along. And the important thing to understand is that the E field is in the center, sort of where everything lines up. If you get into other waveguide modes, weird stuff can try to happen. I mean, there are tables and tables and tables of multiple modes. And the simple way to think about it is RF propagating in waveguide. How many cycles of the wave are there across the length, or across the width or the height of the guide? And there's all kinds of things. And is it you're propagating with a primary magnetic mode or electric field mode? Don't worry about that right now. Just understand that in our primary waveguide mode, this is what we want, and that's why we say WR22 is good at 33 to 50 gigs. It means that over that frequency range, waves propagate in an easily known mode down the waveguide where the electric field is vertical, and we can tap it with an SMA and make a transition out of it, right? All right. Okay, so this is what you find when you go to eBay and you've got a couple $100 you want to dump out or more. The two most common mixers I have seen, and there are others. Tektronix makes a nice little set of mixers, and Hewlett-Packard, Agilent, Keysight, whatever their name du jour will be in the future, also make these nice little set of mixers. Important thing to take away here is that the Tektronix mixers have one SMA port, and Hewlett-Packard did it with two. And what does that mean? Well, we'll find that out. Okay, we'll focus on Tektronix. It's the WM490 series. A very, very good talk was given, or paper, I did not see it, I believe it was just for the SMBS, was by Doug, K6JEY, who did a talk yesterday on Skype. He also did a similar talk to this, and he goes into a lot more detail on some of the Tektronix stuff. So this is trying to build on what he said. There are differences between the two. What Tektronix did is they placed the mixer diode inside the waveguide assembly, and that's all they put inside there. It's very similar to a diode detector mount, only instead of the detector diode, well, it could be a detector diode used as a mixer, but it's usually a single diode in there. And there's a, what did I say here? Put low pass, probably having a fade moment here. Put low pass filter of the detector around 6 gigs. What they did, and I'll get to it in a minute, but the, they use a common diplexer across all bands. And I'll get to the diplexer in a moment. But basically, again, the diplexer is just to allow the local oscillator frequency of the analyzer to get to the diode, say 3 to 6 or 3 to 8 gigs, whatever, and then something below 1 gig to come back out and go to the spectrum analyzer RF input. So that's what your diplexer would be used for. Tektronix made them from, cover basically 18 to 325 gigs. And that's those gold blocks you see. A key trick, though, is that you do really require DC bias on these diodes. If you put some DC bias on there, and when you connect it to the native spectrum analyzer, you can change it from the user interface. You can even apply positive or negative bias. It's hit and miss. You have to experiment to see how the thing works. All right. So how many did they make? They made a lot. And they break it down by standard waveguide band. There's a little bit of overlap in there between some bands. But they're there, and obviously the price goes up exponentially with the frequency range, only because they can. It's also because they spent a little more time in building some of these. They also sold fewer of these than they would down here. Now, come back 5 years from now, we'll see what 5G millimeter wave bands have done. You may find more of this stuff. So what does it look like when you put it together? You've got a Tektronix diplexer. This is the magic box that sort of does it all, if you will, except for the here. This is just a low pass filter from here that goes to the IF port. And then there's basically a high pass filter from here on the first LO coming in. What can you do? And not to scare anybody away, the diplexers usually show up at flea markets and on eBay for maybe $100 to $200. They're really good. I characterized the one that I have, and this port here is good to 1200 megahertz, and this one will pass anything above about 2400 megahertz. DC bias port is on the IF port. On the IF, because that has to go right to the diode itself. All right, now, that's the diplexer. It's kind of boring, but you have to know how it works. All right, this is sort of the business end of things. What are they doing inside here? Well, they took about as simple as approach as you could get. This is a cutaway view, long cut of the waveguide mount. There's your RF input. It's full waveguide size. The waveguide tapers in height, reduces the height slowly down. Hit the spot here where it's at its minimum height. This is where the diode is mounted. The diode, we'll get to that in a minute, is on a metal post that touches the very simple low-pass filter. It's what's called rod and bead filter here that's in the SMA connector. So this allows DC, therefore, to come in. There's no capacitor in here. DC can flow right through the single diode to ground, and we can get RF in and out of here. Within reason, there is a low-pass effect here with the rod and bead. We're trying to stop the RF that's here at, say, 200 gigahertz from coming out here or wanting to go this way. All right? And then what they do on the back of this mixer is they expand the height of the waveguide back to almost full guide height, and they put it with a RF absorber foam in there or some type of load. And what that really does is it's there solely to prevent reflections from coming down here, turning around, and coming back out. Because it's possible that at some frequencies, at a given frequency, if you had a dead back short here or an open, some sort of impedance discontinuity here, you could get a reflection and you get a suck out null. You know, forward power, reverse power, it cancels right here. So the diode would not detect a signal. All right. Another important thing to take away with this. This is their plot or their graph. They talk about a relative conversion loss. They don't mean absolute conversion loss. They say if we specify a mixer to have 30 dB of conversion loss, as I back my LO power down, my local oscillator power for their spectrum analyzer, the loss can go above. And you can see pretty quick that once you come down less than about, +8, +10, somewhere in there, the conversion loss starts to take off. You can try to recover some of that with DC bias, but you're going to be limited as to what you can do. All right, now the inside. There was a Tektronix mixer I picked up, I think I paid $25 for it. It had been through a flood, and the gold is really corroded, and it's just falling apart. But it gave me an excellent opportunity to take it apart and see what Tektronix does in here. And now I know why these things are so fragile and there's so many dead ones out there. It's because on this is the underside of the mixer, the bottom. There's a pocket here milled out. There's another plug that's put in here. There's a couple of set screws that come up to pin it in place. And then there's this funky steel rod that's been cut off after it's been bolted in place, flush cut. You pull that out and rip it apart. Here's the steel rod. What the heck is that? It's a beam lead diode that they glued onto one end of the post. This is me with a manipulator probe going in under the microscope to probe it to see if the diode was good. Because here's what happens. If you drop these things, well, first off, there is no solid connection between the other end of that beam lead diode and the SMA post. It's just a physical touch contact. And then they bolt the pin, put the block down, pin it. Yes, Kent?
As an ex-Tektronix guy, you don't have one diode on there, you have dozens.
Well,
They would probe until they found one.
that was the original design, but these here used a beam lead. It was a single beam lead diode. I know what you're talking about, the point contact whisker diode, right? Like, yeah.
Yeah, so you had
Yeah.
damage to reprobe it.
Right, but they changed the design to this, it got better. The diode got better, but the mechanical mounting of it got worse. So yeah, you're right. The older ones used the point contact similar to what Hughes did on their detectors. This is not. This is just a beam lead diode. So the funky thing that happens is, I don't know how they set these things up. They must have a guy with real precise hands and the optimal amount of caffeine so he's awake but not shaky. And he's got to slide this dowel pin in this mixer that's fixtured all the way in till he gets it, till it just touches, but no more, so you don't fold it up. That's what happened here. This whole beam lead diode, the gold leads on the end started to fold up. So it must have been dropped or pressed or hit at some point in its life. Or the SMA got over-tightened to screw in. There's a lock nut on there. They really could do a little better, I think. But anyway, that's what it is. So I'm in the process of repairing it. I'm going to repair it just like it was. I've cleaned this off. I've glued a new single junction 9101 beam lead diodes. And those who does not know what a beam lead diode is? Okay. I showed that picture. What it is it's a chunk of silicon that has the diode on it, diode junction on it. And what they do to make contacts is they put on these gold ribbons that hang out off the side. And they're opposition. So it looks like a cardboard box that's black with two flaps of the lid open. And those lids are gold. That's the gold wire. So they glue one down in place, and they very carefully touch it up against the SMA and hope that it kind of curls up and starts to fold a little bit. And it does. But you better not try to move it in any position because it'll break free. So that's where I'm going with this. We'll see how it goes, maybe for another talk. Okay, Hewlett-Packard took a different design. And I will tell you this, too. When I worked for MACOM, I got to go to Pawtucket Boulevard, one of the processing facilities in the 80s and 90s from MACOM in Lowell, Mass. I found in their storage warehouse, they had a facility of stored junk, very strange HP 11970 mixer chassis that had been machined, like Tom was talking about, CNC machined. They were all different variants of it. So it appeared to me at some point HP was trying to buy the mixers made by MACOM, or MACOM was proposing to make a better version than what HP could do. I never really found out the backstory behind it because by the time I found it, the people that there worked on it were long gone. So there was a treasure trove of oddball mixers. A lot of the cases were empty. There's nothing in them. It's just a machined block. But it was interesting to know. All right, so HP in their famous 11970 design, they placed the diplexer and the mixer diode into the waveguide assembly itself. Therefore, there's two SMAs. They also use back-to-back diodes for even-ordered mixing. And that means that you have two diodes, and they're anti-parallel, cathode to ground on one, anode to ground on the other. And if you look at another paper that I talked about why that happens, it has an advantage that you only get even-ordered harmonics, so it cuts down on the number of spurious responses you can have on the screen. And they stopped at 110 gigs, WR10. Don't know why, they just did. They do not use DC bias on their mixers at all. So, in fact, if you try it, it probably will make it worse. And like Tektronix, they have a drive level of around plus 16 dBm, plus or minus 2 dBm is their spec. They'll work with less than that. So here's what the schematic of this thing looks like. This is out of the HP document, a manual for it. It's drawn a little funky, but suffice it to say, these two conductors are what would be considered the waveguide. There's they call it a waveguide open. I guess they're trying to mean transition or something there. Anyway, there's our diode pair, back to back. Put a couple arrows there, and those indicate those are back-to-back diodes. So putting DC bias on one of these would only turn one diode on and turn the other one off harder. And you would not normally want to do that. Their diplexer is interesting. They went out of the way to put this nice little diplexer in here and a low-pass filter up to here so that the fundamental RF, again, can't come back down. And there's the cap in there. They drew it as an MIS cap, metal insulating semiconductor. So what did they do for all their bands? All right. These are the ones you'll see all over the web. 11970. Each one of these is the designated frequency range. And I took the data here for the LO cutoff. That's the corner frequency, the low pass filter they have inside the diplexer in it. It's different for each one. And the reason they did that is because of their LO sweep range, and they want to get rid of as many spurs and images as they can. Because think about it, if you were to sweep a signal from, let's do an example. If you were to sweep a signal from 1 to 10 gigs, and we're looking at the actual RF frequency you want while this LO is sweeping. Say you had a 20 gig signal. For every LO, there's an N number for each LO that comes by, and you end up with this screen full of spurs. And there's a software feature in the HP analyzers called signal ident. You ever wonder what that's for? And you basically tell the box, hey, I'm looking in this frequency range. I'm going to lock the harmonic number down, and I want you to tell me all the signals I see on the screen, which is the real one. And how it does it is it sits there and says, okay, very simply, if it's the fifth harmonic and I move my LO by one megahertz, the signal should jump 5 times that, right? fifth harmonic, sixth, whatever the number is. That's how it works out. It sounds confusing, but when you get a chance to use a box or ever get to play with one, it makes sense right away. You go, ah, all right. This was another eBay find. This was an 11970W. This is the WR10 one. This also, for some reason, looks like it's been soaking for quite a while in rusty water. And so I decided to tear it apart. I wanted to find out what makes it work, what it really looks like inside. I have a couple of the other lower band ones that are good. I'm not going to, why tear apart a good one just to see how it works? So I had nothing to lose here. So a lot of cleaning and sort of the walkthrough. There's a ceramic circuit board here. This is your diplexer. There's a couple series capacitors here to bring the LO into here. This is a simple low-pass filter for the IF to flow here. This is the total low-pass filter going to the diode. Where is the diode? You zoom in carefully here. Those are two Teflon blocks they glued down. The diode is actually bridged across here with a little ribbon. It's really hard to see in this because it's all covered in this rust. And the other bad thing they did, wherever this thing was stored, all this nickel plating is coming off. So when I opened it up, there were flakes of nickel plate all over the inside of there, and in addition to rust and crud. So the next step, I had no choice. I had to split the thing apart, and I'm glad I did. This is the inside. It looks filthy. This is part of the waveguide, one half of the waveguide. This is the other half of the waveguide. It does taper. It does taper. They do the same thing that they do. They do a taper. But what's interesting in this case, though, is they only taper from the input all the way back here. They don't retaper it. Their diode sits back here in the end. And what they do inside there is when you put the cover on the back of this mixer, there's a piece of RF foam in there that absorbs reflections, I guess, off the back of the diode because it comes easily over modes when it comes out. I looked at that and went, that's interesting. There's a potential here to make some mixers for hams using that kind of thing. Just a very simple technique. Crew, don't worry about trying to retaper it back down. In fact, so simple that you might be able to take a piece of stock in the mill and by just tilting it and getting the angle right, run the bit by, I should be able to make a piece of tapered waveguide. And if I can find a way to do it at home, line it up, there might be a potential to make some interesting alternative mixers to DB6NT. Yeah, there's all kinds of things you can do. I'm a wannabe machinist, not a real machinist. And it may, well, it's, right. So there's a learning experience here, and I'm learning a lot out of it. Well, when you can't afford this stuff, what do you do? What's to stop me from using a 33 to 50 gig mixer at 200 gigs? Nothing really, right? I mean, performance is probably going to be poor, but, or what about a 24 gig mixer? I'm trying to build stuff on 76. Why can't I just use my test equipment, use the mixer I have, not maybe as the station necessarily. I think Tom said that you guys did that in New England for some of your very early QSOs.
Yeah, the mixer police.
Yeah. The owners wanted them back, right? The mixer's back. But you can do it, and the cool thing is this is an ideal application for a waveguide transition. So there's a guy in Israel on eBay that's been selling these. His seller name, I think, is Pantext, and something like that. Yeah, he's been selling these on eBay. These look to be electroformed gold. He gets several $100 a piece for them. But what I found with this guy who's selling microwave surplus, if you watch his auctions, and I'll probably ruin it because I'll mention this here. If you watch his auctions, he has a lot of stuff, 30, 40 gig multipliers, broadband mimic amps. And he always lists them for reasonable, used commercial price. Every now and then you'll see one for a bid at $9.95. Just to get some interest going. And I think I snagged this for about, I don't know, $60. And somebody listed it and didn't know, but it wasn't paying attention to it. So and then this standard commercial Macom sort of thing, it was Baytron, I think, transition from WR28 down to WR10. So with this, the big takeaway is I'm on the bench, really not really trying very hard. I've been able to use an 11970A easily to 90 gigs and higher. I can do spectrum analysis up there. And the Q-band sensor that I've had, I've used it at over 200. In fact, I've used it at 241 when a decade ago, building gear for that band, how I knew that I was really there. And I was happy with it. I could just see it on the screen. Now, the pitfalls. If you're going to do this, there is one little gotcha you have to understand. Back to this again. Remember, yeah, I can get, as I go higher and higher in frequency above the normal operating range of that waveguide, I can get into multiple modes of propagation in the waveguide. And if you like the n cubed or n to the fourth or n to the fifth power of mixer loss, keep doing this because it'll have an impact. And by that I mean you may end up in a mode here where there is no dominant E field across that diode that's mounted across that waveguide.
At that point.
At that point.
So put an extension.
You can put an extension on it. You can also sometimes loosen the flanges on the front of the mixer and just pull the waveguide flange a little bit apart, just a tiny, tiny bit. You're changing the phase of the incoming RF to the point that you can say, okay, now I can peak it. Yes, sir?
I highly recommend a shim.
Yes, waveguide shims. Yep. Yep, shims are great.
You put some Teflon fishing line down there.
I guess you could. You could do all kinds of things. So you will see an occasional suck out if you try to sweep it all of a sudden at, from 80 to 83, big notch,
That's what the modes are fighting.
That's what modes are fighting, but that's something you just have to accept. It's either that or I'm going to go buy an 80 gig test equipment mixer from somebody. Now, there's another odd effect you'll see. This. This is the 11970. On the analyzer has been set to use standard W band, standard harmonic number. 90 gigs is roughly in the center. And this is the real signal I'm looking at. This is just a 90-odd gig or 89.9 gun running on the bench, just loose. And I put the waveguide mixer and just kind of held it up next to it. Didn't attach it, just held it next to it. And thank goodness for the signal ident feature. Those that are nodding their heads and know what it is, because if I had to figure out which is the real signal here, I would be lost. But still, nevertheless, if I'm close, I can say I expect to be in 90 gigs here. I can start backing it out, and I can start shifting my LO frequency and make sure that it follows the path, the pattern to it. But there's something really weird going on here, and that's an effect of the low-pass filter. The analyzer is trying to sweep higher in frequency, then this 11970A will allow it to go. So it looks as if I've got all kinds of, there's only one real signal here. These are just all the other LO N numbers when you do harmonic mixing. What's going on here? It's not, that's what it's from. So knowing the low pass filter frequency is important if you're going to use a mixer out of band. You got to do the math.
You're not good with the signal ident, or you don't have it analyzed, but it has that. Use one of those old coffee grinder wave things. Find out.
Yeah, you could certainly get yourself close. There's absolutely no doubt about it. So that gets you started. And the last option that I tried, and I tried it very quickly before I came here, so I couldn't have any data on it just per se. But I picked these up these are WR28 waveguide size detectors. They were used just to sample a gun source for some kind of phase locking or something like that. I don't know, it was a piece of junk that I bought and stripped it for parts. And I said, gosh, I wonder how this thing works. Well, son of a gun, lo and behold, without doing anything except putting a waveguide taper on here, I can see up to 90 gigs. I can see that 89 gig gun and a little higher with it. Real easy. So the detector, I don't know what it cost me. Probably cost me, probably the whole assembly was, $150, but there's all kinds of waveguide pieces in there and strip it out. The waveguide transition, I think I bought that for about $100. The diplexer, the Tektronix diplexer I used with it, $150. So for $250, now I've got the analyzer to start with, but I can now sweep, up to 90 gigs, and I can see signals that's there or not there. And the cool thing is you can reuse the parts for another project. Disconnect the waveguide transition, disconnect the detector, use it for another project. So anyway, I brought one of these with me. If anybody's really desperate for one, see me, and maybe we can work out a deal. So in conclusion, always try new things. Always, always, always. When you get into millimeter wave stuff or any frequency band you have an operator on, you will blow stuff up. You just have to accept it and accept that's just part of the learning process. Again, as I always say, experience is something you get only after you really needed it. So once you let the smoke out, once you drop that beam lead diode on the bench, or it goes flying out between the tweezers under the microscope, there's $40 shot. Next step. So, and lastly, do we have any questions from anybody? Yes.
What's the minimum spec analyzer that you need like a rating?
No, because if the analyzer supports if it has some of the old HP portables from the 80s and early 90s, the 8560 series, and I think the 8590 might have covered it. I don't remember. 8560s. 93. Yeah. I guess my point is the CRT based analyzers, the 8560 series. It'll have two SMA ports on the front. One is labeled IF and one is labeled LO. Those are the two ports you want to use. And even the 3 gig or the 6 gig version of the analyzer had those ports on it.
Okay. No, on the old 141T, they could use that external mixer that was biasable, which that little block you didn't mention today.
Yep.
Out there. And you put Tektronix mixers and other things on it. Now you got to figure out the scale. Not
Yeah, you could do it.
6 to 40 anymore, but you could figure the scale out.
Sure, figure it out.
There's a wide range of junk you can use to do it.
Yep. Yeah, cheap.
If I'm not mistaken, the two bench models, the 8566 and 68, I don't believe the 66A had the ports on it, if I recall correctly.
I think the A did, because I have an A that's been converted to a B.
Yeah, it's been converted. It's got
They
it.
only converted the front.
Because I have an A that doesn't have it.
Okay.
I did. Hey, it was free.
Well, I guess the point is there's options out there, and the whole thing is you need to try. I know I've met a lot of guys that want to get into it, and they say, I want to get on 78, but I don't have a 78 gig mixer to see if I'm even on the right band. You don't need one. You don't need one. Start low.
You mentioned using a detector for one of these harmonic mixers. What's your experience on the low-pass filters in the detectors?
Yeah, that's a good point. It's a hit and miss game. I've got some that are abysmal that will barely pass 3 or 4 gigs in, and I would just try it and error, trial and error. I just try it. So consequently, I've got a box full of WR28 detectors. And as I need one for a project, or as a mixer even, to down convert a gun oscillator to, noisily lock it, like we saw the other day, you can use one of those detectors. It's cheesy, but it works. It's cheap. I'd rather put the money into something else. Well, thank you very much.
Thank you, Brian.